Today we're going to take a look at vector-valued functions. So you guys have done vectors before. That's what we did in the last section. You drew some on your tests for me, and most of you did a good job on the drawing of those test vectors. That was good. But we're going to actually do functions now, not just vectors, but vector-valued functions. So the first thing I want to talk about is a definition for what that. All right, so a vector valued function R of t is a mapping from its domain, which is contained in the real numbers, to its range, which is contained in vector space, 3 space, so that for every t in R, the function R of t equals v for exactly one vector v in the range.
V a vector?
Yes. This is what happens when I don't have the pretty type, right? Is that you can't see the vectors very well. I'm going to do an arrow on top.
Yeah.
Yep. One vector v. Okay, that work? We can always write a vector-valued function as R of t equals f of t times I plus g of t times j plus h of t times k. For some scalar functions, f, g, and h. And those scalar functions are called component functions of R. It's f of t. It just is sloppy. Let me try it again for you. That's what it should look like. Okay, so f, g, and t and h are all functions of the variable t. There's nothing special about t. Your book actually mentions this as well. But oftentimes t representing time makes sense in the context of what's going on. So t is the kind of the default that they're going to use here. And then I, j, and k are vectors, just like they were in the last section. So if you want, you can put the vectors on top of those. Your book will write them in bold. Some textbooks, maybe it's worth mentioning, will also put the hats on top of them like that. Have you guys seen that in any of your physics stuff before? Yeah, so some books will do that too. All right, so you ready to take a look at what we're going to do with this? All right, so we're going to do an example. So this is going to be the directions for the next 3 problems. So we're going to sketch the curve traced out by the given vector valued function and then your favorite phrase of all time, by hand. Right? All right, first example, r of t is t minus 1 and t squared. So if you're comparing this to what we did back in section or in chapter 11, what you notice differently is what now? What's different between this and what we did before? There's what? Okay, we've got a vector. How does this vector look different? It's a function. It's got components that have a variable in them, right? Everything we did back in chapter 11 had components that were numbers. You guys with me so far? But now we've got components that are actually variables, or have components of parts of them are variables. All right, so as we're taking a look at this is actually just a parametric equation. So notice this is a parametric equation. With the x component equal to t minus 1 and the y component equal to t squared. You guys see that okay? So if that's the case and x is equal to t minus 1 and y is equal to t squared, we should be able to create basically an xy equation with that information, right? How would we do that? Yeah, we would solve for something. We would solve for t, and the first equation makes the most sense, right? So what is t going to equal? X plus 1, which means then that y is going to equal x plus 1 squared. And that's an equation that you should know how to graph. What is that an equation of?
Parabola.
Yep, it's a parabola. There we go. Okay, it's a parabola shifted how? I mean, it's not just our standard parabola. What is it? 1 unit to the left. So it looks like this, right? Oops, let me draw it differently. But it is parametric in the sense that the t values are going, from negative infinity to infinity. There's a direction with what's going on here. So we need to decide, does our direction look like this? Or does our direction look like this?
First one.
How do you know?
Positive.
What's positive? Okay. This function up here, r of t,
No, the y equals function will be solved.
okay, right here.
Yes, right.
We have to be careful because if the t value were determined a little bit differently, that wouldn't necessarily give us what we're looking for. Is there a real quick, easy way you can think of to know how to draw those arrows? Nope, it's not because of that. That is actually just going to mean that we're above the x-axis. What do you have? Okay, you could plug it in the calculator to watch. That's true. Make a table. You don't even have to do a big table. What could you do? What's that? It has to do with the t values, right? So
You could just plug a couple numbers in.
yeah, so like you were saying with the table idea, Nathan, but we really don't need a whole table. Just a couple of values would be enough. Does that make sense?
0 and 1.
Yeah, 0 and 1 would be great. So let's test t equal to 0 and t equal to 1. So if t is equal to 0, what ordered pair x, y are we going to be at? Negative 1, 0. What if t is equal to 1? 0, 1. So our graph is in fact going to go like this, because when t is equal to 0, we're right here. Yeah? At the vertex, actually. When t is equal to 1, we're actually at the y-intercept. So it is moving from left to right on this graph, and all it took is a couple of points to just verify that real quick. Make sense? Okay, let's try another one of these. This one's not going to look like a parabola, and it's going to have something else going on. Same directions. R of t here is cosine of, 2t. Sine of 2t, 1. So first initial reaction, what are you seeing here that's different than the last problem? There's several things. So three-dimensional, that's the biggest one. We've got trig functions, yep. Anything else?
The z-axis is just constant.
That's important as well. This z value is constant, so it's not going to actually change along the z-axis, right? So it's almost like this is two-dimensional. Agreed? It's just we're going to draw it in 3 dimensions with a solid z value of 1. Okay, anything else? Okay. The double angle, there is a double angle here. It's really not that bad, though. It's not going to affect the graph. All it affects is how quickly the graph does something. That's what double angles do in terms of parametric equations, is how quickly it goes around. So it's going to go around basically like twice as fast if we were actually plotting this, like, if you did your t increments in your calculator or something, it's just going to happen twice as fast. So the double angle is actually not going to hurt us in this one in terms of graphing. Yeah. Okay. Now, on the last problem, what we did is we noticed that x is equal to cosine of 2t, y is equal to sine of 2t, and then in this case we've got a z, which we identified just a minute ago as a constant. And what we wanted to do with the x and the y is we wanted to eliminate the variable t, right? And so the way that we did that on the last problem is we solved for t, and then we evaluated it, or substituted it back into the other equation. Solving for t is probably not our best bet on this one. Because it's sine and cosine, we'd have to use inverse sines and cosines, and that's going to be messy. So what else could we do instead? Close. We don't want to just add them together. Squaring them and adding them together would be very helpful, though. Yeah, so why would that be helpful, James?
Because cosine squared plus sine squared is 1.
Exactly, and this is very important now, and just like Joel had mentioned, these double angles, that they are both in fact double angles. That is, that the angles match. If the angles didn't match, we couldn't actually do this, right? And so the fact that they're both double angles makes it okay. It doesn't really matter what the angles are as long as they match. So we actually do in fact have that cosine squared plus sine squared equals 1, and cosine squared is actually, well, it's x squared in our problem, right? And sine squared is actually the y squared, and this is equal to 1. What's this an equation of? It's a circle. Yeah, I mean, it's an ellipse, but specifically it's a circle, right? It's a circle of radius 1. Okay? So we're going to draw this, and we have to draw this in 3 dimensions. Let's actually write this in, though, just so that we're aware of it. This is a circle of radius 1. And I'm going to note also here, and it's at a height of z equal to 1, right? Like 3-dimensionally. Like we're sort of like in a plane, and then we're just elevating it up 1 unit. It's kind of like we're on the first floor of a building or something like that, and we're on the second floor now. All right, so here's our axis. And we're supposed to be up a height of 1, so there's my z value of 1. And we're supposed to be going out from here 1 unit because it's a radius of 1. So your image looks something like this. I don't draw well in 3 dimensions, so it's okay if you don't as well. But you have the image here where it looks like maybe it looks elliptical because of the 3-dimensional effect that we're having on it. I mean, I get that. And we're raising it up 1 unit. Can you picture it? Maybe not from my picture very well, but can you imagine it in 3 space? Huh?
Yes.
Yes.
Oh, yeah.
Oh, yeah. All right, we got a couple people saying yeah. So imagine taking a pizza platter plate and saying that it has a radius of we'll say 1 foot for the moment, and instead of it being on the floor, it's up 1 foot off of the floor. That's the image you have in mind. Okay. Does that work?
Yeah, it just makes me hungry.
It just makes you hungry. I'm sorry. Okay, let's try one more.
Yay.
Number 3. R of t equals 2 cosine of t. I'll put your little hats on there like you're seeing in some of your other classes. Sine t j plus 3tk. So tell me some things you're seeing as you're looking at this. It's IJK notation, but that's not a big deal, right? No. Yeah, that z position actually has a variable in it now. That's exciting. What else?
You can solve for t.
We could solve for t. That is, we're going to have a z equals 3t. I think that's what you mean, right, Joel?
Yes.
So we could solve this for t if we solved the other ones for t, but I don't think we want to solve either of the other 2 equations for t, do we? Probably not, because they're still sines and cosines. What do you notice about the sines and cosines in the other ones, though, compared to like the last one?
You still have leads to square.
What's that?
When z equals 0, it just leads to square.
Yeah, if z equal to 0, what did you say?
If z equals 0, which have ellipse is.
Okay, so you're seeing an ellipse going on, right? So if you didn't have the t component at the end, this shape would be an ellipse. Does everybody see that okay? It looks similar to some of the other ones we've dealt with in 3 dimensions before. Yeah, so we've got sine of the same angle, sine of t and cosine of t, but we've got 2 cosine of t, which is going to give us an ellipse. So this is going to be an ellipse if we didn't have the z component. So the question is, what in the world happens because we have a z component? Any thoughts? Well, what's z doing? Go ahead, Brandon.
Spiral.
We're going to have a spiral. You're exactly right. The t component's getting bigger, right? I mean, it's getting bigger by a factor of 3. Like as t, goes from 1 to 2, then the z is going to actually increase quicker than that. But it's going to be increasing. As t increases, z is going to increase. So imagine that you're going up the z-axis, right? But you're doing it in an elliptical pattern, so you're going around like this. So you are spiraling, but it's not a circle spiral. It's an elliptical spiral. Okay? So it's a cool shape that I'm not going to be able to draw very well, but we're going to pretend for a moment. All right, so let me put in some axes notations. I didn't kind of been lazy about doing that before, but so we've got this sort of an elliptical spiral. They call it an elliptical helix, just so you know. So this is an elliptical helix. And we're starting out here. Let's just take a look at what happens when t equal to 0. So when t equal to 0, what is my component that I start with? What's my x, y, z pair, or triple? 2, 0, 0. So I'm actually right here to start with, right? X equal to 2, y and z are 0. And then as t increases, it's not especially helpful to use t values that are integers any longer because the t is inside of a sines and cosines. But as we're taking a look at graphing this, it's going to spiral up.
Like a spring.
Yeah, it's going to look like a spring. Or like a slinky. Yeah? Spring. Yeah, I know. Yeah. So we've got an image that looks something like this.
So does it hit the y-axis at 2 as well?
I don't think that it will hit the y-axis at 2, actually. I think it'll only hit, this is not a great picture, but I think you're going to hit the y-axis not evenly because it is elliptical as it's going. So it shouldn't be hitting there at necessarily exactly the same place.
You have to do the inverse sign to
inverse sine of
I
2.
know. I mean, no.
If you wanted to know what the, like if you wanted,
Yeah, what,
You can make z 0, and then you can find the ellipse from just the x and y coordinates squared by.
yes, you could. But the problem is that it's not actually going to hit the y-axis as it goes around. It's going to hit above the, I mean, as it spins, it's not even going to be on the y-axis once it goes around one time.
there's
So-
no y.
Yeah, there's not a y, there, and there actually won't be flat out a y-intercept on this one. That's true. Yeah, because of the way it's spinning. All right, we're going to do one more thing in this section. We're going to talk about arc length. We've had a formula for arc length before. We did it in 2 dimensions, but we're going to do arc length in R3. Does anybody remember what the formula for arc length in R2 was?
Square root of the derivative squared plus
This-
the derivative squared.
Okay, square root of, say again for me.
The derivative squared. And then the other derivative squared.
Okay, so in R2, this was our formula for arc length. We had derived that back in, I don't even remember if it was chapter 10 or chapter 11, but we derived, I think it was chapter 10. We derived that arc length formula. And so what do you think might happen now that we are in R3?
Added in the
Yep.
so another function.
We're going to add an additional component. So we've got the derivative of each of our components squared. And our last one is h prime of t squared. Okay, and I mean, this is coming from our formula r of t, where it's f of t times I, g of t times j, and h of t times k that we had before. So that's where those h, g, and f are coming from. Okay, so we're going to compute an arc length for a problem. Take a look at how that works. We're missing something still, though. Do you know what we're missing?
Interval.
Integral, yeah.
And
And a dt, yep. There we go. Now it looks like calculus, right? Yeah. All right. Did everybody get that written down? I'm sorry, I should have paused for a little longer. We're good? Okay, so we're going to compute the arc length. And r of t is 4 natural log of t, t squared, 4t, from 1 to 3. Excuse me. All right, so what do we need to do?
derivative.
We need some derivatives, so maybe let's just sort of write out the derivatives before we put them into pieces. What's the derivative of the first component?
4, 1 over 2.
Yep, 4 over t, or 4 times 1 over t. What's the derivative of the second component? 2t. And the last component? 4. Okay. So we're going to do an integral. What are my limits of integration? 1 to 3. And we're supposed to do this of the square root of each of these components that we just found the derivatives, each of those derivative components squared. So I have 4 over t squared plus 2t squared plus 4 squared. Does that look okay? This is arc length. Some textbooks call arc length equal to r. Not r, I'm sorry, s. Get the right letter in there. So let's take a look at this and see what kind of simplifying we can do. So we've got 16 over t squared plus 4t squared plus 16.
Common denominator.
Yeah, we can get a common denominator if that's helpful to look at this. I think that might work. a little bit friendlier than just looking at it straight on. So if we get a common denominator, I'm going to get 16 plus 4t to the fourth plus 16t squared. And, well, this is over t squared. That's so far. What do you want to take out, Cameron? Okay, so you want to do...
To become a 2 out of that.
something like that?
Yeah.
Okay. What have I left with underneath the radical then? 4. Plus t to the fourth plus 4t squared. So this is t to the fourth plus 4t squared plus 4. I know you guys are just aching to grab your calculators to do something, but this can simplify really easily. Any thoughts? Do you have an idea, Michael? Got it. So this is a perfect square underneath there, isn't it? So it actually is pretty nice. These are going to simplify, and then we can distribute that 2 over t back through. So this is actually 2t plus 4 over t. Is that right? I think so. Then what? Yeah, we can integrate. What was that?
I'm still not understanding how you took out that t squared.
Yeah, I was listening to.
Which t squared?
Oh, you took out a 1 over t squared.
Yes.
That
Yes.
makes so much more sense. Okay, sorry. Because there was a 16 on the top, and I was like, that's...
I'm missing.
Let me pause right here just to make a comment about, I mean, what you guys have done is fine, but it might be that some of you are going to be able to see what I'm going to show you here a little bit easier. From this point right here, aside from the fact that they've all got a 4 in them, which I can kind of like to ignore on this, but this is actually one of those things that we look at in college algebra. Sometimes students don't always see it very well, but this is a perfect square trinomial just as it is, if I rewrite it like this. Because the first term and the last term are simply things that are squared, and the middle term is what you get when you, like if you could factor this straight from here, this would be 4 over t and 2t, and then they have to both be plus, and if you take a look at the inside and the outside terms, they do in fact multiply to give you the middle term. So you could recognize it from there too, potentially anyway. You see it okay?
Yeah, it happens.
And I mean, if you don't see that, everything we went through is fine. It's quite a few more steps to get to the same spot, but it still works, of course. We do need to integrate this now. So what's the integral of 2t?
T squared.
T squared. And how about the integral of 4 over t?
4 natural log of...
And it's truly supposed to be absolute value t, but our t's are already positive, so we don't have to worry too much about that. Okay, so what do I have? 9 plus 4 natural log of 3. Minus what? 1, which gives me a grand total of
Plus.
8 plus 4 natural log 3.
Is it natural log of 1, 0?
Yes, it is. Natural log of 1 is 0. And if we wanted an approximation, we could certainly get an approximation at this point, right? You could double check that with your calculator and use your calculator to do the integration from the very beginning to make sure that we didn't make any mistakes. I will say that this one is from the back of your book. I mean, well, from your book. And the back of the book's actually incorrect on the value. So there you go. That's what happens sometimes, yeah. The book is, and it's the 4th edition. right? Isn't that awesome? Okay, any questions on that?
Hey, they wanted to read the
The two problems that you're going to do with arc length both have the ability to simplify by hand, so you don't need to use your calculator to solve them. You can use it to check. Yes. All right, let me show you what the homework is. All right, so the homework is page 756. 2, 5, 8, and 13. And then 29 and 30. Six problems. We did 4 problems in class.
Yeah,
And how long did it take us?
an hour, like a half.
I'm thinking maybe 30 minutes.
You're
Maybe.
looking at that clock.
And it doesn't move.